All right, we go. I want to sort of extend. We're moving on to section 10.3 here, and this is where it starts to get sort of the nitty gritty. The next couple sections here. This one is just on tests for convergence, and specifically convergence of a series of positive terms. Convergence of a series with positive terms. And you'll see why this is important in a second here. So we looked at the geometric series. So and a geometric series may or may not fall into this category, but if a series is geometric, we could determine its convergence. We found that the nth partial sum of a geometric partial sum for a geometric series was S sub n could be written as a sub 1 multiplied by 1 minus r to the n minus 1, all divided by 1 minus r. And just because it's a geometric series doesn't mean that it's going to converge, but if the absolute value of r is less than 1, then it did converge. And if you remember, the numerator here, if r is between -1 and 1, it just, as I take it to a higher and higher power, it's just going to start to get smaller and smaller and smaller, so that numerator goes to 0. So this actually will converge to, I'll write it as S sub infinity. I don't know if that's good notation, but S sub infinity equals a sub 1 times 1 minus, times 1 over 1 minus r. Okay, so that's what we did in the last time. So now we're going to look at other series. And we're going to restrict our study right now to series with positive terms. But later on we'll move to series with positive and negative terms. So now consider the series, well, the sequence and the series, corresponding series. The book calls it the P series, I believe. Let's see what they have here. Yep. Consider the P series, and that is S sub n equals the sum from little n equals 1 to big N of 1 over n to the p power. That's not, yeah, that'll work. So we'll just consider a specific one. If p equals 2, then we're looking at this series. Then S sub n equals, the nth partial sum is n equals 1 to big N of 1 over n squared. All right, so this would look like 1 plus 1/4 plus 1/9 plus 1/16 plus plus 1/n squared. And I think we'll just do the specific one in this section, and then for the next one we'll do the more general case and come up with a general rule, sort of like we did with the geometric. The general rule being that if r is between -1 and 1, it will converge. And we'll come up with a similar rule for the value of p here. If p is a certain value, this thing will converge. All right, so we're not going to be able to find necessarily where it converges, but we just want to see if it will converge. So we just want to know, we just want to test for convergence. Double underline that. We just want to test for convergence. So what we're looking at is this sum, n equals 1 to big N of 1/n squared. And we're trying to, we're doing the limit as n goes to infinity, big N, of that thing. And what we're going to do is compare it to this, the integral from 1 to infinity of 1/x squared dx. Okay, and here's why we can do that. Because that graph, the graph of 1/n squared, looks like this. Okay, and I'll put n equals 1. I'll put it someplace nice. Let's just say for giggles that that's n equals 1, just so I have enough space here. Or x equals 1. So the integral that we're dealing with, so this is the graph of 1 over y equals 1/x squared. The integral, the integral version, the integral from 1 to infinity, this guy, is this area, right? But if you think about it, the sequence is also an area. Specifically, the sequence is this area, because, let's see, so that's 1, 2, do another one. I'll clean this up a bit too. Even out these things. Okay? So the sequence is given by the area of these boxes. Because what's the area of that first box? Well, it's 1. I'll write it here. I'll write it below. 1. And then the area of the second box is, if this is 2, 3, 4, and 5, so not drawn to scale here, sorry about that, but this point here is 1, 1, and this point here is 1, since it's 1/x squared, it's 1, 1/4, and this is 1, 1/9, no, I mean 2 comma 1/4 and 3 comma 1/9. All right, so the area of these boxes, if I add them all up, the width of each box is 1, and the height of each box is given by the y value. So the area is going to be of boxes, of rectangles, is going to be 1 plus 1/4 plus 1/9 plus 1/16, which plus dot dot dot. This is our sequence. And whatever you think about these boxes, I know for a fact that the sum total of the area of the boxes is larger than the sum total of the area underneath the curve. So the area underneath the boxes underneath the rectangle is larger than the area underneath the curve. Okay, and maybe you can see where I'm going. Where I'm going is, if the area underneath the curve converges, then so does the area underneath the rectangles. So if we find, evaluate this integral, 1 to infinity of 1 over x squared dx, and see what happens. So that's equal to the limit as b goes to infinity of the integral from 1 to b of 1 over x squared dx. All right, which is, let's see, the limit as b goes to infinity of, put a little box here, so that's really x to the -2, so it's going to be negative 1 over x, evaluated from 1 to b, which is the limit as b goes to infinity of negative 1 over b minus or plus 1. So it's minus negative 1 over 1. All right. So this is, as b goes to infinity, this goes to 0. So that this is 1. So the area is finite, the area under the curve. Area under the curve is finite. Area under the curve converges. And that means that n equals 1 to infinity of 1 over n squared also converges. Note that we don't know where. We don't know the value of that series, but we know that it attains a value. Let's see, I'll write that down. note, it's an important note. All we know that it is that it converges. Note, we don't know the value but we know it exists. Okay, so I think that's kind of cool, and that was for a specific value of p in our series, the p series, which is just 1 over n to the p. So you could probably figure out which ones will and which ones won't converge, but we'll do something more general next time. Okay? So thank you very much for your attention, and good night and good luck.